Welcome everyone. In this video, I want to look at the idea of reaction stoichiometry calculations, and I also want to introduce the idea of yield, or working with percentages indicating something about reactants or products in some kind of fashion. So we're looking at combustion reactions specifically, and we'll look at two different combustion reactions. But for now, the question basically just says we're going to assume that for these combustion reactions, the only products are CO2 and water, and we'll look at the combustion reactions for propane and butane. But right, let's dive in. So our first question asks, how many moles of oxygen are required to fully combust with 2.191 kilogram of propane gas? So our starting point is to write down a reaction equation for propane combusting with oxygen. So that would mean, so let me just label it. So this is for A. We start with, well, propane gas, obviously. So reacts with a certain amount of oxygen to form CO2 gas. Now, of course, this is oxygen gas, and water, also gas. Then, starting to balance it, we look at the number of carbons. So on the left-hand side, we see we have 3 carbons. So we start with the non-hydrogen and oxygen species. So 3 carbons, then we go to hydrogen. We see we have 3 or 8 hydrogens. So that means we need 8 hydrogens on this side. And then we go and fix the oxygen. So on the right-hand side, we have 6 plus 8. That is, well, no. We have, no, my apologies. We have 6 plus 4, so that's 10. So that means if we put a 5 here, then we'll have 5 times 2 gives us 10 oxygens on the left-hand side. All right, so that's a balanced equation. Well, then we can start looking. So how many moles of oxygen do we need to combust with such a mass of propane gas? So we know we can't relate masses, we can only relate moles. So we need the number of moles of propane gas. That's the first thing that we will need to calculate. So to calculate the number of moles of propane gas, we will take the mass of the propane gas and we will divide it by its molar mass of propane gas. The mass we convert it to gram, so that is 2.191 times 10 to the power 3 gram, divided by the molar mass of propane, which you will see is 44.094 gram per mole. All right, 3 carbons for 8 hydrogen, you should get to that value. And then you will get 49.689 and so forth mole propane. Okay, now we have the number of moles of propane. We can go ahead and use our chemical equation to relate the stoichiometries. So what the chemical equation tells us is that 1 mole of propane gas will react with 5 mole of oxygen gas. But what does our reality tell us? Our reality says we have 49.689 mole of propane gas, and that will react with an unknown, or the amount that we are to determine, of O2. So what we do is we cross multiply. So you multiply that value to there, you multiply that value to there, and that will give you an expression. So for now, on the left-hand side, you will see it is NO2 multiplied by 1 mole C3H8 is equal to 5 mole O2 multiplied by 49.689 mole propane. All right. And we want to solve for NO2, so that means then the number of moles of O2 is equal to the ratio of 5 mole O2 to 1 mole of C3H8 multiplied by 49.68. Propane. Right, so I want to stop here for a moment. I mean, you can go and calculate that. You'll see the answer here. So just notice that the units here cancel, mole propane, and you'll be left with units of mole oxygen. So 248.4 mole O2. 4 significant figures, and so many were given in the question. So that's what we have. Right, but the important thing I want you to notice is this fraction here. I want to try and just couldn't get it right, but that's okay. I want you to notice this fraction that I have over here that says 5 mole over 1 mole propane. You don't need to write down this thing here. You can immediately always write down from the chemical equation, you can write down ratios, because how the chemical equation is structured is you have it as all the pluses and the arrows actually are just that I drew there. So you can immediately see it is 1 mole to 5 mole, and then you can substitute that with a per, and you can swap it around for whichever unit you need on top. So if you are calculating the number of moles of O2, then just ensure that the unit that you have on top is mole O2. If you were calculating the number of moles of C3H8, then you should ensure that that one is the one that you have on top, and that whatever the thing that you are cancelling is the thing that you have at the bottom. Okay, so that's how you use the dimensional analysis to quickly get that equation. So you don't waste time writing the same thing 14 times or taking so long. So I'm going to do that from now on, or at least I'll still write the ratios, but I'm just going to write the finished product. Okay. All right, so that's how much O2, the number of moles of O2 required to fully combust with that. And notice the word fully combust. So meaning that means we assume that all of the propane gas is going to react. There's nothing is limiting, nothing is hindering the reaction. Okay. So let's move to the next question. In the next question, we're asked what mass of propane is required to produce 6.5 kilogram of CO2 at a yield of 86%. So now we're given some information about a product, and we're told a yield. So now my question is, what does yield mean inherently? Yield means if we have a certain amount of reagent. So let's say, for example, we had this 49.6 mole C3H8. We expect to produce 3 times as much CO2, right? So in other words, about 150 mole of CO2. But if we're told, so that's what we expect, that is with 100% yield. But in reality, we sometimes form less than what is expected, and that is what this percentage yield implies. That implies that we have to multiply that by a fraction. So in this case, the fraction is 0.86. So we would have to multiply it by 150 by 0.86, and then we would get what it actually is. But what are we given this time? So we're given 6.58 kilogram of CO2. So we're already given the number that is already multiplied by 0.86. So we will have to work in the opposite direction. So what you would have normally done is we would have said, so the question asks us what mass of propane is required. So we would have said, well, we calculate the mass of the propane is going to be equal to, of course, the number of moles of propane multiplied by the molar mass of the propane. Right. And how do we get the number of moles of the propane? Well, that is related to the number of moles of the CO2. And how is that related to the number of moles of CO2? It's through the reaction equation, but the number of moles of CO2 is actually related by the amount of the yield. So we will have to take into account some sort of factor here which upscales it eventually by 100 over 86. And you'll see how we get to this point eventually. So let's start by calculating how much CO2 actually forms. So the mass of CO2 is what's given to us. Mass CO2 is given as 6.56 kilograms, so that's 6,560 grams. That then means the number of moles of CO2 is of course equal to the mass of CO2 divided by the molar mass of CO2. And that's going to be 6,560 gram divided by 44.008 gram per mole. Gives us 149. Why is my pen not right? 149.063 mole CO2. Okay, that's how much CO2 forms after multiplied by 86%. So what we now need to determine is how much propane does this relate to? And we do that through the reaction equation. So of course we know 1 mole of propane relates to 3 mole CO2. We currently have 149.06 mole CO2. And we want to know how much propane that would have related to. So from this information, it means the number of moles of C3H8 is going to be equal to, so you can immediately write it, 1 mole C3H8 forms 3 mole CO2. How much CO2 do we have? 149.06 mole CO2. It's going to give us a value of 49.68 mole C3H8. Okay. But what is this amount assuming? This amount of propane assumes that all of this propane produces CO2. So now the question is, by how much extra do we need to increase the amount of propane that if we were to multiply the number that we actually get by 0.86, we would get to the same number of CO2. So basically, this assumes 100% yield. So therefore, at 86% yield, what we say is we require this number of C3H8 multiplied by 100 divided by 86. That's how much we need extra. Because in principle, so let's just call this required, we need to put a little bit extra because we actually need to multiply the value that we expect by 86, by 0.86. So this will give us a value then of 57.776 mole C3H8. Okay. So basically what this says, so let's do it the opposite way around. If you had 57 point that mole, how many moles CO2 would this produce? Right, so we produce 3 times that. 3 times that is roughly 58, so that's 150 plus 24. It would be roughly 174 mole of CO2, right? That's a lot more than the 149 that we produced. But if you multiply this value by 0.86, you roughly get to 149 mole. And that's what we wanted to get to. We wanted to know what value of C3H8 would produce a value of CO2 that if we multiply that value by 0.86, we would get to a value of 149 mole. So you can do it in different ways that you want to get to, but that's the logic. Right. And we're not asked the moles, we want to know the mass. So we want to know what is 57.7 mole C3H8 mass. So you're just going to quickly calculate the mass. Its mass is up, molar mass is up there, it's 44.094 gram per mole, and you should get a rounded value to 4 significant figures of 2.548 kilogram of propane. Okay, so what percentage yield essentially tells us is we get less than what we expect. So now this says we want to get so much CO2. How much extra do we need to put into the system to ensure that we still get so much CO2? And that's essentially what the question's asking. Okay, right. Let's move on to the butane questions. So I just need to get to a new page here on my side, the side where the magic happens that you can't see. So what mass of water is produced by the combustion of 1.46 kilogram of butane? And then we're asked how many hydrogen atoms is present in this mass of water. It's a bit of an interesting question, but anyway. Right, so now our first step here is to write the combustion reaction of butane. So we have C4H10 gas. Combustion means it's a reaction with oxygen, gas. We're told at the beginning the only products are CO2 gas and water vapor. Right, so we always start balancing with the carbons. So there's 4 carbons on the left-hand side, so we need 4 on the right-hand side. Then we look at the hydrogens, 10, so we make this a 5. And then we look at the oxygens. What is happening with the oxygens? So there's 2 on the left, but there is currently 8 plus 5, so that's 13. So something that you can do is you can go say 13 over 2, but we know you can't, you can leave it as such here because the question doesn't ask, right, the balanced equation. But in principle, what should you do if you have a fraction? Then you multiply the entire equation throughout by 2. Right, so to get rid of the fraction. So we just multiply everything by 2. So this stoichiometric coefficient, all of these are going to double. So then it means 2 reacts with 13, gives 8 and 10. Okay, so that's how we balance it. We're given a mass of butane, so 4H10, which is 1,460 gram, which is going to give us the number of moles of butane as 25.120 mole butane. Okay. Of course, I mean, you should be able to calculate the molar mass of butane and then get this number of mole. Right, and then we want to know how many moles of water forms. So we can determine, because we want to get to the mass of water, right? What mass of water? Yes. Get the mass of water from the number of moles of water. So we see 2 butane gives 10 water. So let's try and write it this time just directly from the equation. So the number of mole of water is equal to, so we want to end up with water. So 10 mole water divided by 2 mole butane. That's from the equation. And how much butane do we have? We have 25.120 mole C4H10. It's going to give us a value of 125.6 mole of water. Okay. And so we can calculate the mass of the water, which is, of course, the number of mole of water multiplied by the molar mass of water. Molar mass of water, just as a note here, it's 18.015 gram per mole. And you should get a rounded value to 4 significant figures of 2263 gram water. Okay, so that's the mass. Now let's look at the other question. The number of hydrogen atoms. Number of hydrogen atoms. How do we get that? How do we relate anything to atoms? Well, what we do know is we know how many molecules there are in 1 mole. That's given by Avogadro's number. So we know we have 125.604 mole water. And we know that Avogadro's number tells us that there is 6.022 times 10 to the power of 23 molecules in 1 mole of a substance. Right? This is from Avogadro. So, if you know that there are so many molecules in a mole, then it means that the number of water molecules must be the number of moles of water multiplied by this ratio, 2 times 10 to the power 23 molecules per mole, or per mole water, or whatever substance you're working with. So plug in the number of water, so then you should get a value of 7.563 times 10 to the 25 molecules H2O. And now we know how many molecules of H2O there are, but that's not what we asked. We asked how many hydrogen atoms there are. And how many hydrogen atoms do we have per molecule of water? There are 2. So we have 2 H atoms per molecule. H2O, so again, it's a ratio, so you can say 2 H atoms per molecule of water, and you can use the dimensional analysis, but essentially it means that number multiplied by 2. So the number of H atoms is equal to twice the number of water molecules rounded to 1.51. 3 times 10 to the power 26 hydrogen atoms. Okay. And you see they're all just ratios. There's so many molecules per mole. There's 2 hydrogen atoms per molecule. I mean, it's all ratios. Even reaction equations are there's 2 moles per 10 moles that form, 2 moles that react per 10 moles that form. All reaction equations, everything in chemistry are just ratios. Okay, so that's represented by this mass of water. Right. What mass of carbon dioxide is obtained when 3.867 liter of air, which consists of 23.3% oxygen, reacts with butane? Given the air density under these conditions is that. So what in principle are we given? We're given the amount of oxygen. So we're told that the amount of air, so we're given a volume of air, and we're given the percentage that oxygen makes up of that air, and we're given a density for the air. So we can calculate the mass of air, and then we can calculate the mass of oxygen of that, and then of course we can get the number of moles of oxygen, and we can relate oxygen and carbon dioxide. So the mass of air is equal to the volume of the air multiplied by the density of air, which equals to this 3.867 liter and 1.30 kilogram per liter. Will give you a value of 5.027 kilogram air. Now 23.3% of this mass is oxygen. So that means the mass of oxygen is equal to 23.3 divided by 100 multiplied by the mass of air. Give you a value of 1171.29 gram oxygen. So I just quickly converted the kilograms to gram and then multiplied. So from that, we can get the number of mole of oxygen, right? Because we can't relate masses, we can only relate number of moles using chemical equations. Mass of oxygen divided by the molar mass of oxygen. Molar mass of oxygen is 31.998 gram per mole. Gives us 36.60 mole O2. Okay, so using the reaction equation, so we balanced it up here, it's butane. So 13 mole of oxygen produces 8 mole of CO2. In other words, 8 mole CO2 is produced for every 13 mole of oxygen that reacts. So how you write it is the number of moles of CO2 is going to be equal to 8 mole CO2 is produced for every 13 mole O2 that reacts. You can also do your cross multiplication or whatever. But we have 36.0 mole O2. And so you'll get 22.526 mole CO2. Okay, the mole O2 is cancelled, and you're left with that number. And finally, we ask for the mass. So the mass of CO2, of course, equal to the number of mole of CO2 multiplied by the molar mass of CO2. And the molar mass of CO2 is 44.008 gram per mole. We should get a value here of, so it's 3 significant figures because if you look at 23.3 as well as the density, 1.30. So this time it's 3 significant figures. So you get 991 gram CO2 is produced. Okay. So that's it for this example. It's a bit tedious, but it's basically to teach you the ideas of the ratios, how to work with the percentages, how to get comfortable with those concepts. Right, thank you for watching, and I hope to see you in the next video.